ways. In particular, by Aristotle, through the argument of symmetry, that there should be a cold land in the south in order to balance the land in the northern hemisphere. So this map was done in 1570, and you see, at that time, people didn't have any knowledge about the South Pole, so they just drew this by imagination. Okay, and the South Pole was discovered in the 19th century. Oops. And this is a map in the early 20th century. And this map was actually not 100% correct. And after people discovered the South Pole, more and more people try to explore the land, and nowadays you can see this kind of modern map of the South Pole. What I want to say here is that the South Pole is predicted to exist through the argument of symmetry, and the Higgs boson is predicted to exist through the argument of symmetry breaking. So now we have observed until this year, we have seen more and more data confirming or telling us that the new boson at 126 GeV is very likely the standard model Higgs or standard model like Higgs. So the natural question is it really just the standard model Higgs, or it is purely standard model like Higgs? In other words, whether there's something beyond a larger Higgs sector for us to discover. And in fact, if you think about it, for the fermions, we have 12 flavors, and for the gauge bosons, we have 4 kinds. So it looks like nature or God prefer to repeat. When he finds something useful, something good, he likes to repeat it. And why not Higgs? Okay, now we see one Higgs, why not second, third, and so on? So maybe the Higgs boson, this 126 Higgs boson, GeV Higgs boson might be a portal, or maybe even the only portal for us to go to discover the beyond standard model Higgs. Because you see, we have searched for the fermions, the 4th generation, for quite a long time, and we found nothing. We have searched for the Z boson, Z prime or W prime, and up to 2 eV, we have seen nothing. So maybe it's the Higgs sector, the scalar sector, that can lead us to new physics. Okay, so here's a quick outline of my talk. I will mention briefly the simplest version of the triplet model, and then I'll introduce you the Georgi-Machacek model and the glider phenomenology. Okay, so this is the simplest version of the triplet model. Sometimes people call it type 2 seesaw model. It was introduced in around the 80s, and the basic idea is to introduce a complex triplet. And in this case, you will not only have neutral and charged singly charged component, but also a doubly charged component that's very different from what people usually have in the new physics models. And so here you have the normal, the usual standard model Higgs potential, and then you have the potential terms for the triplets. And in particular, the motivation, of course, is not to introduce a doubly charged Higgs. The motivation was to give mass to the neutrinos through such a term. And so such a term can give the Majorana mass to neutrinos. So that was the motivation, a different source of mass for neutrinos. And people start to study how the new charged Higgs bosons decay, and people have found that the decay patterns actually depend on the triplet valve. So if the triplet valve is below something like a 10 to the minus 4 GeV, the dominant decay modes for the doubly and singly charged Higgs bosons are the leptonic ones. If it's above 10 to the minus 4, then it's dominantly a pair of gauge bosons, or in this case it's more complicated, it includes a pair of gauge bosons, or W and H, or top and bottom. So my collaborators and I had studied this a while ago, and we found that if the triplet valve is small, we can look for the the signals of this model by looking at 4 leptons, namely 2 pairs of like sign leptons, or at least 3 leptons, 3 or more leptons. In this case, assuming a 14 TeV machine and the luminosity of 10 inverse van der Waals, you can reach up to, in this case, is up to 550 GeV, and in this case, you can reach up to about 600 GeV. And in fact, the CMS had already searched for such particles. Of course, they only look at certain scenarios. For example, there are 4 typical benchmark points and also 6 special cases. Like, for example, this one is assuming the doubly charged Higgs will decay into a pair of like sign electrons 100%. Okay? And the others are they are different, like this BP4 means that democratic, it will decay into all 6 possibilities equally. Anyway, so if you look at this 95% search bound, you find that typically the low bound, the mass of the doubly charged Higgs boson is a low bound around 400 GeV typically. So it looks like it's pushing to higher and higher masses. So we started to think another scenario, namely for large triplet valve. In this case, as I just told you, the doubly charged or singly charged Higgs bosons will dominantly decay into a pair of gauge bosons, or more complicated for the singly charged Higgs boson, it's slightly more complicated. So we looked into this possibility, and assuming, for example, let's look at this blue curve. In this case, we assume a triplet valve of 55 GeV, and we for the signals, we impose the forward Jez cut. Then again, assuming 8 TeV or 14 TeV configuration and 10 inverse van der Waals, it can reach up to either 450 GeV or 800 GeV. This scenario has not been, well, as far as we know, has not been seriously studied experimentally. So that's why we wrote a paper and proposed this for our experimental colleague to perhaps look into such possibilities. But there's a problem with the simplest Higgs triplet model. It's the following. Well, the first, it's about the constraint on the triplet valve. The first one is the lower bound. There's no problem with the lower bound. Here we require triplet valve to be greater than 1 eV. That's mainly because from the knowledge of the neutrino mass. But there's a problem with the upper bound. That's this rho parameter. Experimentally, we found that the central value of rho is slightly greater than 1 with small error bars. However, in this simplest version, rho is less than 1. And so if you require that in this model, rho falls within, say, 95% confidence level of the experimental number, then you'll get something like triplet valve cannot be greater than a few GeV. So remember that in the previous plot I showed you 55 GeV, that's unreasonable in this model. So fortunately, we found there's another model proposed by Georgi-Machacek and Machacek that was proposed in the mid-80s. And what they do is, in addition to a complex triplet, they further introduce a real triplet, and they can be put into this form. And so by putting in this form, I think from the lecture by Professor Zupan, you know that this kind of matrix form is particularly useful to identify the global symmetry. So here you also have the SU2 left cross SU2 right symmetry, and they transform like this way. And now if we assume there's a line vacuum expectation value for the triplet fields, then the symmetry breaks down to the custodial SU2 vector. And in this case, just like in the standard model, you can guarantee rho equal to 1 at tree level. And if you look at, people have looked at, Gunning and the company, they have looked at the radiative corrections and see how that affects this rho equal to 1 requirement. It found that in this model, it is as natural as the standard model. In other words, if you think the standard model is natural to keep growing to 1, then there's no problem with this model as well. Well, here I just quickly flash the general Higgs potential. It's like this. I don't want to bother you with the detail. But I want to mention this term is required, just like in the simplest Higgs triplet model, this term is required to induce the triplet valve by the standard model electrically symmetry breaking. Okay, so now under this SU2, custodial SU2 symmetry, you can classify the triplet field into a 5-plet, a 3-plet, and a singlet. And the standard model doublet field can be classified into a 3-plet and singlet. So here we write down the 5-plet fields are like this in terms of the chi and xi field that you saw in the 3x3 matrix. And the 3-plet is here with a tilde because there could be some mixing. So before rotating to the mass eigenstates, this is temporary, the field's like written like this, and here's the singlet. And for this H50 is CP even, this one is CP odd, and this one is CP even again. The point is that because of the custodial symmetry, each multiplet, the fields in each multiplet are degenerate in mass. So that's one feature of this model. So if you want to verify the custodial symmetry of the model, you can do it by checking the mass degeneracy of these fields. So among each multiplet. Okay, here is some detail telling you that, as I said, the field with the tilde is not a mass eigenstate. You have to rotate to the mass eigenstates. And here, this is the rotation matrix. And the notation here, H is, this tangent theta H is basically the ratio of the triplet valve over the doublet valve. And of course, they should add up to be the 46 GeV that we know. And this alpha angle is the mixing for the CP even states. Okay, one thing, if you take the decoupling limit, namely you let the triplet valve go into 0, then you will find, you can calculate the mass spectrum, and you will find that, these are some parameters in the model, but anyway, the bottom line is that among the 5-plet, 3-plet, and the singlet, you will find a mass relation. So knowing 2 of them will determine the left one, the other one. Okay? And this is the standard model like exposure mass. And even if not in the decoupling limit, this is still a good approximation. So we will make use of this relation in our later calculation because we can eliminate one parameter from the model. Okay, here I'll show you the YUKAWA interactions. This is from the new YUKAWA interaction that I show you in the case of the simplest Higgs-driven model. So you can see, for example, this term tells you that the doubly charged Higgs field can decay into a pair of like-sign charged leptons. And the second part is the usual YUKAWA interactions. And one particular thing is that for the 3-plet, only the 3-plet can couple with the quarks, the standard model quarks, through mixing, through this mixing angle, and also here. And the other H1 and H5 do not couple with the standard model quarks. So that's one feature of this model. Okay, here I list all the gauge-gauge scalar couplings. In particular, for this one, this is a singly charged Higgs boson in the 5-plet coupled with W and Z bosons. Usually, in the 2Higgs double model, there's no such vertex. But in this model, this vertex is allowed at tree level. It only is suppressed by this sign of theta H. Again, tangent theta H is the ratio of the triplet valve over the doublet valve. So as long as you have a big enough triplet valve, then this is non-negligible. Okay. Another thing is that you see here, there's no 3-plet. So the 3-plet does not couple with the gauge bosons. Okay, that's another feature of this model. now comes to the phenomenology. For our numerical calculation, we impose such constraints like vacuum stability and unitarity, and also the positivity of the mass. Here, I just show you some plots as examples, just show you that we do take them into account in our later calculations. And also another constraint from the R sub B observable. So here we plot the triple, okay, so here you can get an upper bound on the triplet valve. So 1 sigma bound is this, and 2 sigma bound is this as a function of the three-plate mass. So you see that we can still, for a wide range of parameter space, we can still take V delta to be a few tenths of GeV. And you can also impose the B to S gamma constraint, but we found that this is not as stringent as this R sub B constraint. Okay, so these are the constraints that we take into account. Now, for the phenomenology, we consider three mass hierarchies. Here, delta M is defined as mass difference between the 3-plate and 5-plate. So there are three possibilities. Either this is equal to 0, or greater than 0, or less than 0. So different hierarchies. And we fix the mass, well, at that time we fix it at 125, and this particular mixing angle alpha is fixed to be 0. So we are left with only three parameters: the triplet valve, the 3-plate mass, and this mass splitting. Okay. And now, here we plot we divide this space V delta and delta N space into different regions, because in different regions, these charged Higgs bosons have different decay patterns. For example, I told you that if V delta is smaller than a certain value, those charged Higgs bosons mainly decay leptonically. But if it's greater than a certain value, it decays into the gauge boson pairs, right, like this. But if there's a mass hierarchy, it's more complicated because you can have cascade decays. But what I will show you is, I will concentrate on this region 2. In this region, there's these charged Higgs bosons will couple to the gauge bosons more strongly, and that's how they decay in this region. So there are many production channels. Wow, so fast, how time flies. One is Cheng-Wei process, that's like this. And this kind of process is basically gauge interaction, mediated by gauge interaction, so it's independent of the triplet valve. There's something called mixed Cheng-Wei process. It's this, because you produce H5 and H3 at the same time. In this case, this cross-section is proportional to cosine 2 theta H, and this is, compared to the Cheng-Wei process, it is more suppressed. In particular, if you go to a larger triplet valve, then this is even more suppressed than the Cheng-Wei. Then we have vector boson fusion process. That's important because now, because of the stronger coupling between the gauge bosons and the Higgs, this becomes more dominant. It is proportional to the triplet valve squared. And likewise, there's a associated vector boson fusion, namely you produce one H5 along with another weak gauge boson, Z or W. This is also proportional to the triplet valve squared. And there are also YUKAWA processes, but it's suppressed by the, well, there are two possibilities. One is gluon fusion, and the other one is the T-channel production. The T-channel production is proportional to 10 theta H squared. And if the mass of the triplet is smaller than the top, you can have production through the top quark decay and so on. Anyway, the important channels for us are the vector boson fusion and the associated vector boson fusion, which were not important in the simplest Higgs triplet model, because in that case the valve is small. But here we're considering order 10 valve, it becomes dominant. And mixed Cheng-Wei process is also important because you can produce H5 and H3 at the same time, and that allows us to study the mass degeneracy of the triplet. in these plots, I just show you the importance of different kinds of production channels. For a wide range, the most dominant one is the vector boson fusion, the red curve, and then the mixed Jhongli, and then associated vector boson fusion. So in the following, we just consider one particular example. The triplet mass is 150, mass split is 10, and triplet balance is 20. That is, again, in the region 2 that I showed you before. And we calculated different branch ratios, and we found that the bottom line is that we find that we can use the vector boson fusion and the associated vector boson fusion process together to fix the multiplet of H5 and mixed Jhongli to fix H3. So here due to the limit of time, I just quickly show you the different channels, the signal events. And the bottom line is that for the 5-plet, for different charge states, we are looking for these signal events, and we also consider the backgrounds, imposing the typical cuts, and also, since this is vector boson fusion process, so you have 2 forward jets, so we impose additional requirements that the jets are widely separated, and this is because from the transverse mass distribution, we found that we can also gain the signal over background by imposing this cut. Next. So here are the results. For the doubly charged Higgs, we found that we can, this is in cross-section in units of femtobarn, and we assume 100 inverse femtobarn luminosity for either 8 or 14 TeV configuration. So we found that the significance for the doubly charged Higgs is no problem. It's big enough. And for the singly charged, it's like this. So you can see the improvements in the significance. And for the neutral one, unfortunately, even if we impose d jet beta, we cannot get a 5 sigma discovery. And now for the 3-plet, again, these are the channels, and here are the simulation results. For the singly charged and the neutral one, you get the significance are good enough. Okay, here's the summary. So I just told you the Georgi-Machacek model was motivated first by being able to give mass to the neutrinos, and also to satisfy the rho equal to 1 constraint. And the model has the following features. First, the particle spectrum is like this. There's several new Higgs states. In particular, because of the custodial symmetry, you have mass degeneracy among the multiplets. And of course, there might be some electromagnetic corrections, but we expect that this is an order of a few hundred G MeV, so that's not a big deal. And we found that the 5-plet and singly couple to weak gauge bosons, but not the fermions. The 3-plet is up the other way around. And for we consider the large valve case, I show you the result for simulation result for 20 GeV. And we found that vector boson fusion, associated vector boson fusion are important to determine the mass of the 5-plet, and the mixed Jhongli process is useful for the 3-plet. And that's it. Thank you.
When you allow the other guys to have also larger event, okay, so the main necklace with the standard model of Higgs coupling, it will be magnetically retained.
I'm sorry, you said?
When you have allow all these other guys to have a large event, right?
The large triplet valve?
Yeah.
Yes.
So then the standard model Higgs coupling will be magnetically retained. The YUKAWA coupling might be.
No, it's here. Let me quickly go. So the YUKAWA coupling is here. Okay, so we assume alpha equal to 0, so this is 1, but yes, this part will be affected. This, yes.
So,
That's right. So what we are doing now is to try to fit the current data and study what are our allowed parameter space as far as the couplings are concerned. Yes.
And also the W coupling from the WZZ coupling will
Yes.
also change.
Yes, definitely. Yes, you're right.
So that maybe has a model.
Yeah, we are working on that.
Yeah,
at the
okay.
moment, yes.
Super small comment. So
How super?
yeah, it's very small. The bound on the triplet web.
Yes.
So actually the BB bar mixing is slightly, it's a little bit stronger than the B to S gamma, but RB is still stronger. So you're in that here. There's a BB bar mixing bound as well.
Oh, you mean the constraint from BB bar mixing?
Yeah, it's a bit stronger than B to S gamma, but it's still worse than RB.
Okay.
I think
That we didn't check.
that's why.
Okay, so you're saying that it could be stronger than R sub B.
It is stronger than B to S gamma, but it is worse than the RB.
Okay, so good. So this is still good enough. Okay, thanks.
So you were going through it very fast, and I missed the part.
I thought I spoke slowly.
What's the associated media for production? Associated media production, how do you tag it?
Okay, so for the associated VBF, we have this, for example, this production, and we assume this one decays hadronically, and this one, of course, decays to a pair of W's,
Okay.
and then that decays leptonically. So they have the, oh, I didn't mention, in the end, they have the same signals.
Okay, so it's actually associated production, but with one of the vector goes from decay to two jets.
Right.